Radar echoes are unlike anything NASA's seen from a natural object. If this fast-moving interstellar traveler is really exhibiting engineered behavior, the stakes aren't just scientific, they're planetary. But why would a messenger from outside our solar system act like it has a mission? The truth starts with the night 3I Atlas was found, July 1, 2025. The Atlas telescope array in Chile flagged an object moving against the background stars, a faint, fast blip catalogued at magnitude 14. Initial software tagged it as another long-period comet inbound from deep space. Gemini South and Hubble joined the confirmation run, each logging the same coordinates and a dust halo just visible in the stacked exposures. The orbit solution computed overnight placed the newcomer on a hyperbolic track, retrograde, high inclination, and unmistakably interstellar. The Minor Planet Center assigned the provisional label 3I Atlas, making it only the third known object of its kind after Oumuamua and Borisov. Early calculations showed a benign passage. Closest approach to Mars was projected at nearly 2 million kilometers with no threat to any spacecraft or surface mission. Astronomers noted the object's speed, nearly 87 kilometers per second relative to the Sun, but found nothing else to suggest urgency. The first spectra, limited by distance and faintness, showed a coma dominated by carbon dioxide and hints of water vapor, matching the template for a typical comet. For the survey teams, 3I Atlas was a curiosity, a rare visitor, but one that fit the expected mold. The discovery log closed with routine remarks. No one yet suspected what the next weeks would bring. August 7, 2025. JPL's orbital dynamics team, joined by Harvard's astrometry group, began recalculating the path of 3I Atlas after a week of new positional data. The object's speed, locked at nearly 87 km per second, put it among the fastest bodies ever tracked, fast enough to cross the Earth-Moon gap in less than 80 minutes. At this velocity, even a minor nudge could mean the difference between a safe flyby and direct impact. Over days, covariance plots tightened. The predicted miss distance to Mars shrank, not by millions, but by hundreds of thousands of kilometers with each refinement. Analysts flagged non-gravitational residuals in the FIT, tiny systematic deviations that resisted explanation by solar heating or standard comet models. The object's trajectory bent closer to Mars's orbital plane, with each update compounding the sense of unease. Dynamicists ran delta-V simulations. A change as small as 10 km per second delivered over weeks, by outgassing or unknown means, could tip the flyby into a collision course. The numbers left no room for comfort. Every new solution amplified the stakes, as if the object was threading a needle through the solar system, one where the smallest thrust could retarget an entire planet. The question sharpened: was this random cosmic chance, or the signature of intent? August 14, 2025. The Mars Reconnaissance Orbiter Science Unit logged a sudden doubling in 3I Atlas's apparent brightness, a spike that arrived with a surge in ultraviolet output. The event, captured in back-to-back photometric sweeps, was neither gradual nor chaotic, just a clean twofold jump in intensity, as if the object had thrown a switch. Spectroscopy teams on Earth and at Mars began sifting through the data. What surfaced was not a random outburst, but a cadence. Every 17 minutes, a fresh burst of carbon dioxide erupted from the nucleus, each one timed with uncanny precision. The jets did not scatter at random angles or drift with the rotation. Instead, each pulse aligned neatly with Mars's orbital plane, as if following a preset schedule. The pattern held for days. MRO's ultraviolet sensors caught the same rhythm, a train of spikes repeating with mechanical regularity. Amateur astronomers tuning their cameras for the green wavelengths reported 3 needle-thin tail filaments pulsing in unison, always pointing toward Mars. The triple stream, faint but persistent, matched the 17-minute cycle logged by the professional observatories. No known comet in the solar system has shown such disciplined, clockwork venting, least of all one traveling at nearly 90 km per second. For the planetary science teams, the anomaly was not just in the numbers, but in the choreography. Outgassing this regular, this directional, suggested a kind of energy management beyond the reach of solar heating or surface cracks. The question pressed in: was 3I Atlas simply the most extreme comet ever tracked, or was it operating with intent? September 15, 2025. On a secure line from Goldstone, an anonymous DSN technician relayed a single sentence to a colleague: "No iceball bounces radar like that." The first deep space radar pings aimed at 3I Atlas as it neared Mars returned echoes that rang sharp and hard, signals that in decades of comet tracking had only ever come back from metal. The cross-section modeled from the raw data implied a dense, compact body orders of magnitude above the returns from dust or porous rock. Estimates run through the Planetary Defense Modeling Suite put the mass near 10 billion tons. If the core was solid, as the radar hinted, it could span nearly 400 meters across, comparable to the largest metallic asteroids, yet moving at a velocity no asteroid in the inner solar system has ever matched. Impact simulations ran overnight. At 57 kilometers per second, a direct strike would release energy on the order of 2 million megatons of TNT, enough to excavate a crater 60 kilometers wide and 5 kilometers deep, reshaping a region of Mars in seconds. Debris models traced ejector cones stretching well beyond the Martian atmosphere, threatening orbiters, relays, and even interplanetary space. The numbers left little doubt. This was not a regional hazard, but a planetary one. As the radar data circulated, a second leak surfaced. ESA's Mars Express, in a review of its image archive, flagged 3 glinting points near the object, each maintaining a perfect triangle frame to frame, as if holding station beside 3I Atlas. The geometry was too precise for random debris. Analysts debated the possibility of fragments, escorts, or reflections, but the pattern persisted across multiple exposures. For the defense teams, the evidence was stacking: mass, energy, and now geometry, each defying the template of a natural comet. The threat was no longer theoretical. The question now: what or who was steering this interstellar visitor toward Mars? September 19, 2025. In conference rooms from Darmstadt to Tsukuba, directors from the European Space Agency, Roscosmos, the China National Space Administration, and the Japan Aerospace Exploration Agency convened on a single encrypted channel. The agenda was blunt: coordinate response to an object closing on Mars at 57 km per second, with a critical window for action measured in days, not months. The ISO Object 1 Task Force formed by unanimous vote, the first multinational unit dedicated to an interstellar hazard. Expert panels split over tactics. Some pressed for a full intercept. Others advocated passive observation, citing the unknown risks of intervention at such velocity. Technical teams mapped out every feasible trajectory correction, but the object's speed left little margin for error. Each agency committed assets, tracking time, simulation clusters, rapid response protocols, while legal teams drafted the first joint directive